Hello friends, MoNaCo here, second to last video in our Redox unit. This lecture is about voltaic cells. That's a scary name for something that we use every day, which is called a battery. So the batteries that we're going to be looking at in this unit they don't look like a typical battery. But they are indeed batteries. So we'll know how to show the direction of electron flow, the parts of a battery cell, and where oxidation and reduction occur in the cell after this particular lecture. Batteries are all around us. They power our devices in our lives, but how do they work? That's the focus of this particular lecture. They work through oxidation and reduction reactions being placed in separate cells and forcing the electrons to travel through a circuit in order to do some work, like power a device to get from one side of the cell to the other side of the cell. Basically, we take the oxidation and reduction half reactions and separate them so that the electrons have to travel through a wire in order to do the redox reaction. And as they travel through the wire, they do stuff like power our devices. So electricity goes from the positive to the negative terminal of the battery, and that's how it kind of works. So two types of cells, voltaic and electrolytic. We're going to focus on voltaic for this particular lecture. They have some similarities, though. They both involve redox reactions and chemical reactions which involve the flow of electrons. Both involve the flow of electrical energy or current measured in volts. That's kind of how we measure volts current in physics class. But we don't really do much measuring of volts in chemistry. Both have two electrodes, conductive surfaces where oxidation or reduction occur, called the anode and the cathode. These are like the positive and negative terminals of a battery. Every battery has them. Oxidation or reduction occurs in each half cell. So voltaic and electrolytic cells both have all of the following things in common: anodes, cathodes, oxidation, reduction, transfer of electrons, period. How do we remember what happens where in what cell? Well, reduction happens at the cathode, red cat, always at the cathode, and that's where the ions gain electrons. So ions from a solution will gain electrons that are given back to the solution, and back to the ions, sorry. Oxidation occurs at the anode. That's where a metal loses electrons. Electrons flow through a wire from the anode to the cathode. How do you remember that? Well, anode starts with A, cathode starts with C, so this is kind of alphabetical. So electrons travel from the anode to the cathode through a wire. Oxidation happens at the anode, reduction happens at the cathode. Let's move on and see what an actual cell looks like. This is the image that is ubiquitous, meaning very common when we're talking about batteries. We have a half cell 1, the first half cell where one reaction occurs, and the half cell 2 where the other reaction occurs. They're connected through a salt bridge so that ions can move. And they're also connected through a wire where electrons move. And this voltmeter can be replaced with any electrical device like television, remote, iPod, iPhone, etc., and will be run through the movement of these electrons. Now, table J is used to help predict which direction the electrons will spontaneously flow. When you close this switch, the electrons are going to be flowing from the most active metal to the least active metal. So draw arrows in the direction of the wire. So we go from most active to the least active. I like to use green to show electrons flow. And if we look on table J, lead versus silver, lead is more active. So the electrons are going to flow in this direction. So we're going to put arrows pointing the direction of electron flow. Flow from the lead to the silver. Now, based on your answer above, which would be the negative electrode and which would be the positive electrode? Well, anodes flow to cathodes. So this is the anode. That was on the previous page of notes. And this is the cathode. So the cathode is positively charged, and the anode is negatively charged. So the PB equals the negative one, and the AG equals the positive one. Explain your answer to number 2. Well, electrons flow from anode, positive most, no, that's negatively charged terminal, sorry, negative, and most active metal, to cathode. That is positively charged and least active metal. That's your explanation for why one is charged and the other is not. At which electrode or in which half cell does reduction occur? So reduction is gaining of electrons. Gain electrons, reduction. So if electrons are traveling from the anode to the cathode, all these electrons get out here and then they go right into the solution. So reduction is gaining electrons, and that happens at the cathode. Red cat. Cathode. At which electrode or in which half cell does oxidation occur? That is at the anode. An ox. An ox, red cat. Which electrode is the cathode? The cathode is the less active metal, so that's the Ag. And which one is the anode? That's the more active, that is the lead. So electrons don't flow to the cathode, they flow through it to the ions in the solution. That's why the cathode itself never becomes negative. One of the things that's always hard to wrap your brain around is if the electrons are moving from the anode to the cathode, they go straight into the solution. They don't actually build up on the cathode. Because you say, well, if they're going to the cathode should become negative. That's not the case. They're going through the cathode into the solution to reduce Ag positive plus 1 electron to become Ag silver. And while on the other side we have Pb metal becoming Pb positive 2 plus 2 electrons. Those 2 electrons are the ones that are traveling through the wire. And this lead is the anode itself, and it becomes, and that becomes a lead positive 2. So on one side you have lead losing electrons to the wire. On the other side you have silver ions gaining electrons from the wire. Let's see if we can get onto the next page here. So voltaic cells spontaneously convert chemical energy into electrical energy or electric current. Basically, a voltaic cell is a battery. Wet cells are what we just saw. They have a liquid, they have ion solutions. They've also got pretty heavy and dangerous anodes and cathodes. This is the type of battery that's in your car or the bus or the truck. They are large, heavy batteries that produce a lot of current, and they can be very dangerous because the electrolytes is usually a very strong acid, very dangerous. Now, a dry cell is what we're more commonly familiar with. Those are those alkaline batteries. They got the positive and the negative terminal. The lithium-ion battery in your cell phone is a dry cell. So these are more portable, they're lighter, they're safer to use, but they don't produce quite as much electricity. So it would be great. I mean, you could run your cell phone on a car battery for like years without having to charge it, except that car batteries are extremely heavy, not easy to use, and dangerous. So we've used this dry cell technology to simplify it. A salt bridge. This is the part of the battery that allows the ions to flow back and forth. So if we look back to our cell, right here, we got this salt bridge. Circuits must be complete. If you think back to your robotics or any kind of training you've had in circuits, if the circuit isn't closed, meaning a loop, like so, then electricity won't flow. So that's what the salt bridge does. It kind of completes the circuit so that electrons can flow through the wire and ions flow through the salt bridge. A cathode spontaneously attracts electrons to it. That's the positive electrode in a voltaic cell, and it's where the reduction occurs. Red cat. Reduction at the cathode. Less active metal from table J is the cathode. It's the less active one. The anode is spontaneously losing electrons to the cathode. This is the negative electrode in a voltaic cell where oxidation occurs. An ox. An ox, anode, oxidation, reduction, cathode. And again, the more active metal from table J is your anode every time. So at this point, you should be able to identify some of the basic parts of the voltaic cell. Galvanic cells, many synonyms there. The direction of the electron flow based on table J. The parts of the cell like the anode, cathode, salt bridge. Where oxidation and reduction occur in the cell, like in the half cell 1 or the half cell 2. Which side does what? Plenty of practice on this material because that's the only way we're really going to understand it, labeling up these diagrams repeatedly. So thanks for watching. Talk to you later.